So my name is Zhangling Lu. I'm a physics professor at National Taiwan Normal University. I'm very excited to be here today for the physics fight and welcome all of you enjoying this morning's competition. First of all, I would like to introduce our jury. And the first one is Professor Lin Jianpeng from Lujing Guanxia. And the second one is Professor Liu Yiyu from Taiwan Tech. Welcome. And the third one is Professor Xu Fangqi from Lianhe Daxue. And the fourth one, Professor Lin Wenqing from NTNU. And the final one, Professor Zhang Minjuan from Furen University. So we have a reporter, opponent, and reviewer. So the team captain introduce your team members' name and their grade and their interest. Please.
I'm the captain of Wave 2, and he is Lian from Wave 2.
So wait, each one, okay.
Oh, he is Lian Chu.
Which grade?
Grade
11. And what's his interest? Physics. Okay. The second one.
He is from Wave 2, and also 11.
11. Okay.
And his interest is Chinese.
Chinese. Okay, good. Okay.
And
The third member.
he is Liu, and his interest is playing video games. And he is also 11.
So he's interested in playing video games. Good. Okay, the final.
Oh, he is Yu Xuancheng, and he is 11th grade, and his interest is
Programming or coding. Okay, good. Okay, so welcome the reporter. Okay. And the team member, the team captain for the opponent, introduce your team member's name and their grade and their interest.
Hello everyone, we are S501 from Concordia Middle School, and I am the captain Zhang Yuoyan, and I'm in senior 2, and my interest is in drawing. And,
Drawing?
Yes. And he is Typt, which is also in senior 2, and his interest is in playing basketball.
Playing basketball.
And he is Wang Guan, also in senior 2, and his interest is in physics.
In physics, okay, the second one,
And
physics.
also the only girl in our team is Hong Yujia, and he's in senior 1, and his interest is in reading fiction novels.
Okay, reading a fiction novel.
And also he is Chen Lifu, also in senior 1, and his interest is also in fiction.
Okay, physics. Okay,
Thank you very much.
welcome. Now, reviewer, the team captain, please introduce your team member's name, grade, and their interest.
Hello everyone, we are Lin Zhongqi from Indian High School. So for me, my interest is singing, and my name is Zhang Yijun, and his name is Chen Antai. His interest is in quantum computer.
Quantum computer.
Yeah, computing, and also he is Zhang Yuyu. He's also interested in quantum computing.
Quantum computing.
And she is Zhang Minjuan, and her interest is in drawing. And he is Yu Xingzi, and his interest is in programming.
Programming. Okay, so welcome. So now we start this morning first round. The opponent challenged the reporter for the problem. So 1 minute.
opponent would like to challenge problem number 9, like whisper.
Okay, the opponent will challenge the reporter problem number 9, light whisker.
Yes.
The reporter accepts or rejects the challenge. You have 1 minute. Accept or reject? Problem number 9. Reject. Reporter rejects the opponent. Problem number 9. The opponent challenge another problem.
The opponent would like to challenge problem number 7, the dynamics.
Okay, the opponent wants to challenge the reporter number 7, B dynamics. Accept. Okay. So, consideration of the reporter, 5 minutes, and Dean, please write down your representing name on the blackboard. Thank you.
同学，你赶快把东西吃完，好不好？我们在比赛，其实，而且在防疫期间是不能用吃东西的。
我放一下 repeat， 换一下 repeat。
Huh? So reviewer, you will change?
Yeah, change.
Okay. Jiang Yixuan. Now Yuan Yun do the presentation 12 minutes, please.
Okay, so good morning. I'm the reporter from Legal Senior High School, and I'm going to present the dynamics. And these are my contents of the presentation. So I'm going to introduce you the phenomenon, and then the theory, and our experience, and our conclusion. So as a prompt beat, a circular groove rotates about the vertical diameter. A small bead is allowed to roll in a groove on the inside of the hoop, and investigate the relevant parameters affecting the dynamics of the bead. So after reading the prompt, we believe that vertical and roll are the two important parts of the prompt, and so our theoretical calculation will be based on these two known conditions. Now this is the phenomenon of the bead dynamics. So as you can see, the bead indeed go off when the hoop starts to rotate, and this is done with a high-speed terminal. To know the dynamics of the bead, we applied Newtonian mechanics and Lagrangian mechanics to our theoretical calculation. For the Newtonian mechanics, we balanced the gravitational force with n cosine theta, and we attributed the centripetal force to n sine theta, and we derived the third equation from the first two equations. So from the equation, we can know that the equilibrium angle is 0 or r cosine negative d over r naught omega squared. And also when the omega is smaller than the square root of negative d over r naught, the bead will be in a stable equilibrium. Okay, so to know the dynamics of the bead, we also apply Lagrangian mechanics. And from these two equations, which are the Lagrangian equations, we can know that the Lagrangian equals to these, and we believe that there is a friction force, and we assume that the friction force is proportional to its speed. So we can derive this equation from the Lagrangian equation. So by solving the equation, we got the same result. The equilibrium angle would be at 0 or r cosine negative d over r naught omega squared. And when the omega is smaller than the square root of negative d over r naught, the bead will be in a stable equilibrium. And later we noticed that the bead has a volume, so we considered it as a rigid body. Because it's a bead with volume, it would roll and it has a rotational energy. So we included the rotational energy here. And after we the calculation again, and we got this equation. So for the equilibrium angle, the only difference is that the R0 in the previous page becomes RT, and which is the distance from the center of the hoop to the center of mass of the bead. And others are the same. And this equation shows that the fact that the bead is a rigid body affects its motion. And since we got the theoretical condition, we started our experiment. And these are our experiments. We used an EV3 and a new camera and a circular hoop in our experiment. And this is a diagram of our experimental setup. So we used a computer to control the speed of the servo motor, and we put the camera in the hoop so it can film the way the bead goes. And also we use a smartphone camera to monitor the screen of the EV3 so we can know the hoop's angular velocity. And these are the three types of beads we use: a metal bead, a marble, and a wood bead. Then we got the result. The first diagram shows the equilibrium angle for the hoop with a radius of 9.8 centimeters. And as we can see, the theoretical value is a black line, and the metal bead is closest to the theoretical value, while the wood ball is the farthest from it. Then we did the experiment again, and this time we used a hoop with a radius of 11.5 centimeters. And we got a similar result. The metal bead is the closest to the ideal value, and the wood ball is the farthest from it. And the ideal value here, we used the R0 in the previous page. So as shown in the previous page, we use the three types of beads we use are these. And the radius of it is 0.47 centimeters, 0.81 centimeters, and 1.07 centimeters. And we believe that the results that are presented is caused by the radius difference of the bead. So then we did the analysis again, this time using the RC and NR equation. And we can find out that the experimental data is closer to the ideal value this time. And this is the equilibrium angle for the metal bead, and with the 9.8 centimeters bead. And also, this is the value of our equilibrium angle for the marble. And we can also see that it is closer to the ideal value than it is in the previous calculation. And this is the result for the wood ball. And at first, the wood ball is far from the ideal value, but this time it is much closer, and we think it is almost the same as the ideal value. And this is a diagram for the same experiment, but the hoop with a radius of 11.5 centimeters. And this is for the marble. And then this is for the wood ball, and they are all close to the ideal value we calculated. So next, we try to know the motion of the bead before it gets into equilibrium. And the blue line is for 12 omega of the hoop. And this experiment is done by the hoop with a radius of 9.8 centimeters, and we use a metal bead. And the different colors of the lines of different colors represent different angular velocity of the hoop. And from this diagram, we can know that the beat is in a depth oscillation before it reaches equilibrium. And also the larger the angular velocity is, the smaller the oscillation period is. So then we simulated the motion with program for drawing the graph for the equation. And when we type in these equations and put our values, the mass and other values in the equation, we can draw this diagram. And we found out that it is similar to our experimental results. And to be more specific, this is the comparison between the prediction of omega equals to 60 radian per second experiment, and the red line is our experimental data. Also, in conclusion, the equilibrium angle of the bead would be 0 or r cosine -3 over RCM omega squared. And before equilibrium, this is the equation that shows the motion of the bead. And because of a friction force that is proportional to the velocity, the bead will be in a damped oscillation before it reaches equilibrium. And also, the larger this value is, the smaller the period of the damped oscillation will be. And that when RCM omega squared increases, the equilibrium angle increases and the damped oscillation period decreases. And this is the end of my presentation. Thank you.
Thank you. So now we move to the question the opponent to the recorder, and the recorder answer the question. 2 minutes. Yes, start.
First question for reporter. Can you turn your page left at 3 volts in 3 beat? Okay. As I see, are the material of the volts the same?
No, they are not.
They are not the same. Okay. So you change the mass and the radius of the ball at the same time, right?
Yes.
Okay. Okay. Next. Please turn to your experimental data.
Which is
Just say it. Okay. Can you explain the vertical and horizontal arrow bar?
Because our experiment is not done very perfectly, so the motor of our experiment was sometimes not in the same angular velocity.
In your experience, do you set the angular velocity as a constant or variable? Is it angular acceleration or velocity?
Velocity.
Velocity, no acceleration. Okay, thank you. Please turn to your theory. Let's consider density.
Are you talking about this equation or?
The following page, please.
This?
Okay, just forget it.
Sorry.
Did you try to release the ball when the angular velocity stays at constant? Release the ball at a certain angle that is not from the bottom.
Our experiments are not really done at the angle of 0 because.
Okay, thank you.
Okay.
Thanks, okay, so move to the preparation of the opponent. 3 minutes. takes the floor and makes about 4 minutes and discuss with Anyun, please.
Hello everyone, hello honorable judges and all the competitors. I'm from TSLB and today I'm going to cover number 7, beat dynamics. And here's the problem statement. A circular hoop rotates about vertical diameter. A small bead is allowed to roll in a group on the inside of the hoop. Investigate the relevant parameters affecting the diameter of bead. And the opponent thinks that we should make both about the motion of the bead in different conditions and the effect of different parameters. And here's a structure that opponent thinks should solve the problem. And first, investigate the motion of the bead on the hoop, and which is the oscillation and the equilibrium position of it. And next is the angle of oscillation of the bead. And we use a series to use the boundary equation and the damping. And next, we investigate how the different factors affect the equilibrium position, which has the equilibrium analysis, rotational speed, and the radius of the hoop. And next is the strong and weak point of the reporter. First, he did a clear observation video and a phenomenological explanation, quantified theory, and clear derivation of the theory. First, what she had done good is that he didn't let the camera move as the whole system moving, and he can control the variable, and next didn't consider the condition of the spin acceleration. And next, the opponent did good on the clear diagram of the experiment setup and consider the damping, and she has a clear demonstration of the oscillation. And next, but he didn't analyze the frequency of the oscillation of the bead. And next, he changed two variables at the same time, which I think is very not good. And his lack of the variables, only the radius and the mass, and he didn't explain the error derivation from the theory. And here's the point I think we need to be discussed in the next phase. First is the experimental setup. The initial angle, if can be fixed first, and the rolling speed, which is the constant velocity or the constant acceleration. And next is the observation about the bead motion, and we want to discuss about the equilibrium position, which is the angle of it on the hoop. And next, the rolling and the acceleration motion of the bead. Next is the effect of damping. And then here's the theory part. I want to talk about the equilibrium position and the Lagrange equation she used, which has the energy transformation and the potential energy and kinetic energy. And next is the force analysis. I want to talk about the effect of the friction, air drag, and the normal force. And next is the oscillation. I want to talk about its frequency, amplitude, and the decay rate of it. And next, I want to talk about the effect of different parameters, which includes the potential speed of the hoop, and next, the initial angle of release is in the bottom on the side of the hoop at first, and the rotational radius of the hoop. And next is the hoop. I want to discuss about its diameter and the material of the bead and the hoop. Will it cause different friction coefficient or the deformation? And upon want to skip to the next phase.
Okay, so to move the discussion. Okay.
First, can you draw the force analysis on the bead of the rotating hoop? Yes, the force that's force on.
I have here the normal force would be here, and there would be a gravitational force.
Yeah. Only this.
When it is in equilibrium,
When it's in equilibrium.
we can consider these.
Well, the problem statement has mentioned that it's in the rotational hoop, so the opponent thinks that the force should add a horizontal force. You add this in your Lagrange equation, and you say in the equation you want effect, but the hoop is rotating, right? So you will have this force, right?
Can you explain what that force is doing?
What?
Is there a certain other force?
This is for here's the bead, right? So when it's rotating, then we look it from bottom or from the up. So the bead will rotate like this, right? From up to up the bead will look like this, right? Then
the net worth of these words. So we think the net worth of these words would be
Network.
yes, the net worth of these words are the cost of its interpreted words. Yes.
Okay, thank you. Please turn to the screen data. Can you explain why your error bar is really the same?
Oh, because our error is mostly caused by the vibration of the motor and the error of our when we look at the angle of the beat. So we found out that the motor's angular velocity would vary at more
Okay,
at
thank you. How many times you do the experience?
this experiment we did
Twice.
oh no, once.
Once.
Yes.
If you do this once and one more, you have error bar.
No, our error bar is not the error bar we use usually. It's the error of our motor vibration and the experimental
Okay.
error.
Next. You said you let the motor spin in the constant angular velocity, right?
Yes, we tried it.
But you have angular acceleration too, right? But so can you predict the motion of the feet when the hook is rotating at angular acceleration?
You mean before it reaches a certain angular velocity?
Yes.
Oh. No, we mostly focus on the motion of the beat after it reaches a certain angular velocity because we found out that
Okay, thank you.
okay.
Next, because as I mentioned in the previous, there will be a centrifugal force, right? So the beat won't just have the force to let it go up. You will have the force to make it move in a horizontal.
Yeah, okay.
So can your device observe the horizontal displacement of the beat? Your hook is look like this, right?
Yes.
So can your experience setup observe the horizontal move of the beat?
Oh no, our beat is bit in the hook, so it wouldn't have a horizontal movement.
Okay. Please turn to page 26. The blue one is your theory, right?
Yes.
And why will it start earlier than the experimental data?
Because our experimental data is from the time when the angular velocity becomes constant. So we didn't, as I mentioned before, we didn't analyze the motion before it gets to the certain angular velocity.
Okay, thank you. So can I give you advice?
Yes.
I think you can release the force when the hook is rotating at the angular, particular angular velocity you want.
Yes.
So, but you didn't do it, right?
Yes.
Okay.
Sorry, we will do it next time.
So the parameters you do is the mass of the beat and the radius of the beat and the radius of the hook, right?
Yes.
How about the angular velocity function?
Oh no, we changed the angular velocity, so it is shown here. So the blue one is the angular velocity of 12 radian per second.
Okay, thank you.
Yes.
I want to ask about when does this motion achieve equilibrium?
We think it reaches equilibrium in this part.
And why will it damp a little?
No, we think the damp is caused by the vibration of the motor since we couldn't really control the motor to be at a certain angular velocity.
Okay, thank you. if the ball if the beat steps as you button, and theoretically, whenever how the fast your rotational hook is, the beat won't go up.
Yes.
The ball will be goes up because of the vibration of the motor.
No, because we actually gave it a initial angle. Like we put it at 5 degrees, so it would go up. Because when we put it at 0 degree, it often stays at the bottom.
You release the ball first, or you turn the motor on.
We put the bead in the hoop first, and we put we sometimes put something in the bottom of the hoop so we can put the bead on that device so it can stay at 5 degrees when it starts to rotate.
Then why can't you do the experiment about the initial goal release to when the angle of D is constant?
Can you say that again?
You say that you can control your angle of release while the hoop is rotating.
No. We put it here and then we start to rotate.
So
Yes.
when you put it here
Yes.
and you start to rotate, then when did you release the bead?
Oh, we start to rotate the hoop after we put the bead in the hoop.
Of course, you start to rotate after you put the bead in.
Yes.
But when did you release the bead?
Before the hoop starts to rotate.
Then if you release the bead before the hoop starts rotating,
Yes.
then the bead will have this kind of motion, right?
Yes.
Then
We put something here to prevent the bead from staying in the angle of 0. So we start, after we put the bead here, we start to rotate the bead.
okay, thank you. This central rotation then has 3 beads. I can see this pretty obvious that the 3 beads is different, and the mass and radius change at the same time. Can you explain what will affect the result?
According to our theory, we think that the mass of the bead wouldn't affect its equilibrium angle. So we did this experiment first, but we think we can improve our experiment if our control our variables better.
There are different materials, so their friction might be different.
Yes.
Then you use the Lagrangian to calculate the motion and the equilibrium angle, right?
Yes.
So can you just use the force and combination to solve the problem?
Do you mean the Newtonian mechanics?
Yes.
Yes, we can find the equilibrium angle from Newtonian mechanics as we shown in our presentation.
Okay. If there is a possibility that the bead will rotate to the side while the motor is spinning, will there be a possibility? You release the ball at this side, and
Yes.
when the hook is rotating,
Yes.
then will it have the possibility that the hook is going to the side?
It wouldn't go to the next slide and
Okay, so we'll go to the next stage. Opponent summarize this discussion 1 minute.
Okay, I'm the opponent from here, Sophie, and here's the summary of our discussion. First, we talk about the initial goal release, and the reporter says that they use something to block the bead from it to roll down. And next is the theory. The reporter says they can not just use Lagrangian, but they can also use force analysis to calculate the equilibrium and the motion of the bead. And next we talk about the force that will work on the bead, and the opponent said, because of the setup of the reporter, so the bead can move in the horizontal motion. So I think that is not good for the reporter. And next, because they use the different bead, so their friction coefficient will be different. So they change the mass and the diameter at the same time.
Okay, thank you. Now the question of the reviewer to the reporter
electronic, but because their setup is not a flash service. So.
And second, then as the force analysis graph you have drawn, how about the static friction force there? Because you have added the static friction force into your theory, right?
No, it's a connected friction. Yes.
Okay, so then we do think it will be a constant.
No, it is proportional to the speed.
And then, so then I want to ask the question about the problem statement.
Yes.
You told us to investigate the dynamics of the heat.
Yes.
Please change it to your data of the damping motion of the heat.
Yes.
So, I know your experiment is about this, that situation under a specific angular velocity.
Yes.
But what's your answer about the damping motion before?
Before the equilibrium.
Yes.
The damping motion is caused by the friction that is proportional to its speed.
Okay. So what is your answer about the damping motion before it comes to equilibrium?
Before what?
What is your answer about the beat before it achieves the equilibrium? What situation do you think that is?
The beam will oscillate in a group, and because the beam it was slightly a little bit, so they will have two kinds of friction, and because of the damping, so the oscillation amplitude will decrease over time, and the beam will finally start at the equilibrium angle.
Okay. So then I want to ask both of you guys, do you think it's pure rolling when the beat is rolling on the beat?
I think it's not a pure rotation, but we analyzed it. We did a theoretical calculation with the pure rolling, and we think maybe if we, I think it's too difficult to, it's nearly impossible for we to consider the splitting of the beat, so we didn't include it in our presentation.
So do you think it's pure rolling?
No, it will slide a little bit, so I think the reporter should do an analysis about the sliding situation, whether the angle is bigger than a particular angle, so the beat will slide a little, and the reporter didn't see that.
Okay, the last question. I think that's what affects the rotation of the beats on the beat? Okay, sorry.
It's now preparation of the reviewer. 2 minutes. Be careful. Okay, so the reviewer take the floor.
Okay, I'm the reviewer from Jincheng High School. So today's problem is the beat dynamics. So this is the problem statement. I want to elaborate more. So I think the problem statement told us to do is the first, change the parameters. Second, the theoretical model. The third one is the control and effective experimental setup. Fourth is to explain the phenomenon. The fifth is the key parameters that we should change. Then the summary of the report I want to say is that about understanding the problem, the qualitatively interpretation of the problem, and that's very good, and they know how to apply the two methods. And the theoretical analysis, they quantitatively analysis with the two model and got the same answer with these two ways. And they told about how to find the equilibrium. And also the experimental confirmation, they explain the charts, but I think that should be more explained. They should explain the chart. So this is the mirrors. The first one, they have already controlled the experimental setup, and that's very good. The second is the phenomenon explanation. And the third one is the response to the problem brought up by the opponent. And the possible next step, I think that there's no theoretical equation that talks about the dynamics of the beat when it's before it's achieved the equilibrium. The second is they didn't explain the ideal value that is different from the experimental data. And the summary of the opponent, the key insights of the opponent in the short question is that they changed two parameters at the same time, and they asked for the explanation of the charts, and also they said the angular velocity as a constant, just like she has just answered. The force is that they release at the ball at a certain angle. So this is the merits of the opponents. So I think you point out the experimental errors, and that is very good. And the second is that the good short question people. And the third one is the clear explanation of the pros and cons. But I think there are possible next steps. It needs more explanation on our own ideas. So this is the discussion analysis. So the problem raised by the opponent is the force analysis of the dynamic motion. But the reporter's response is that they consider it the equilibrium points. And we agree with the opponent since that the gravitational force, normal force, and the centrifugal force for the acceleration system should be considered. And the discussion analysis too is about the predicted angular acceleration. However, they didn't answer, so I think it should be talked more. Then why did there is a dam there? So just that I have asked. So the reporter's response that the model didn't control it at a certain angular velocity, and our view is it must be the motor or experimental mistake. I think that it can be improved more. And also the how will the beat go up? And the reporter's response that they have the initial release at a certain angle. And our view is the theory needs to be considered the initial angle there. So the three beats are different, and the reporter said that it should be improved next time. So this is our reviewer's points. So the first one I asked is the beat will go up, and they have already answered our question. And the second one is about the static friction force and the kinetic friction. And about the damping motion, I think they can discuss more about the damping motion's periods. So I think that this discussion can be well improved more, but I think they have a good discussion well. Thank you.
Thank you. So now will be concluding remarks of the reporter.
Okay, so I'm going to start my concluding remarks. So the first one is that we had considered the centripetal force, but it is not an actual force that acts on the object. It is a force. It is a net force of the normal force and the gravitational force. And then we started the beat with an initial angle before we started to rotate. So the beat will go up, and we did do the experiment when it is at zero angle, and I can show it to you later. And theoretically, only the radius of the beat will affect the equilibrium angle. So we didn't really control the other parameters as in our experiment, but we can improve it next time. And even the theory says that the mass wouldn't affect the conclusion. We still can control the mass of the bead to ensure the completeness of the experiment next time when we do the same experiment. And if the bead was put in 0 degree, it won't move, and I will show it to you later. And we can improve our experiment surely because there is some mistakes in our experiment. So this is the slow motion we film when it is at 0 angle, and it wouldn't really go up. And also we considered other possibility of the friction, and we found out that every friction is not suitable for our experiment. So we believe that the friction force is proportional to our velocity.
Okay, thank you.
Thank you.
So now the questions of the jury. So please, Professor
I
Ling,
have the same question to all three of you. And friction sounds important. Can you tell me that if the friction is extremely small, what will happen?
If it is extremely small, the motion of the bead would be like this, and it wouldn't have the bend.
How about the others?
I think if the friction is extremely small, then the ball won't have rotating on the hoop. So there the energy will less, the Lagrangian will have minus the energy from the rotation of bead. Because the bead is sliding, yes, friction is less.
I'm a little bit agree with the reporter, however I have something different with her. Is that I think that if the friction force is extremely small, it will finally achieve the equilibrium. However, the damping period of it will become the damping time of it will become much longer before it's achieved it.
any other question from jury? Okay, Professor
I have
Ling.
a question. Okay, suppose we change another circle, right?
Yes.
Okay, a big one. Okay, the position of this ball will left or down. Because in your chart, omega equal to 16 and 20,
Yes.
almost around 60 degree, around 80 degree, right?
Yes.
Okay, because your radius of your circle may be 11. Okay,
Yes.
but suppose we change a big one circle.
Yes.
Okay, will it left or down?
Do you mean the equilibrium angle?
Yes.
So, as shown in our conclusion, the equilibrium angle would definitely be affected by the radius of the hoop. So we think that the larger the hoop is, the equilibrium angle would be larger.
For me, I think the answer is when we change the bigger hoop and the position of the bead will become much lower since their radius depends on the hoop's radius and the length the ball holds. So when we calculate these two things and the bead's position will become much lower.
My thought is that the equilibrium angle will be higher, but it won't be bigger than 90 degrees whenever we change the radius to be. It will only achieve 90 degrees if the radius is infinity, but it's not possible. So yeah, the equilibrium angle will be higher, but won't be bigger than 90 degrees because this is the upper sine function.
Questions? More questions? Comment? If you have one 90 seconds. Okay, reporter, could you go to your page 24? Yes. You mentioned the for the 16 omega, you get a smooth curve.
Yes.
Okay, but the other two, green and blue, you have a small oscillation.
Yes.
It's due to.
I think it's due to our motor because this time the motor is quite stable at the certain angular velocity because we monitor the angular velocity and we think we just change the battery of the motor so it can function better.
Okay.
But it still has a little vibration, but we can't see in this part because it's too small for us to see.
Any question? Okay, so analysis of gradient for the system. The jury ready? Okay, the first, the score for the recorder. 7, 8, 7, 5, 8, 5. Okay. The next, the score for the opponent. 6, 7, 6, 7, 7, 8. And the score for the reviewer. 7, 7, 8, 6, 9, 6. Okay. 10分钟休息。Okay. So we take a 10-minute break, and each team change your position. Thank you very much. The presentation of the report.
Okay, so honorable judges and other competitors, I'm the reporter from Typt S501. Today I'm going to report problem number 6, irreversible Cartesian diver. And this is a problem statement. A simple Cartesian diver is placed in the low vertical tube filled with the water. And increasing the pressure is the tube forcing Cartesian diver to sink. And when it reaches a certain depth, it will never return to the surface, even if the pressure is changed back to its initial value. And I think I will mainly focus on what is the main cause of the diver to be irreversible, and the parameter that will affect the critical volume of diver's sinking depth. And this is my presentation outline. So first, for preliminary experiment, I will talk about the observation of the reversible and irreversible situations, and the variation of the inner water level. And for theory part, it's based on the Pascal principle and Boyle's law, and we use Bernoulli principle to make sure that our theory is correct. Then for experiment, the parameter will be the length, the outer base area, and the mass of the diver. And for discussion part, we talk about the boundary condition and the current depth of the diver. So for preliminary experiment, this is the observation video of the diver when it is reversible. So you can see that when we add additional pressure, the diver will sink down to the bottom of the tube. And when you release the additional pressure, the diver will flow back to its initial height. And for the reversible situation, we also add the additional pressure like a red line. So the diver sinks down to the bottom, but when we release the additional pressure, the diver won't go back to its initial height, just like the video showed. And this is the variation of the inner water level. So you can see that in the first part, the slope is bigger, and in this part is caused by the additional pressure and also the water pressure. And for the second part, the variation of the inner water level here is smaller, and in this part, it's affected by the water pressure. And for phenomena explanation, so according to the Boyle's law, we can know that the pressure multiplied the volume will be constant. And when the diver sinks, the volume of air column, which is here, will decrease. So the buoyancy will decrease as when the diver is sinking down. Then we need to talk about when will the irreversible situation happen. So well, the additional pressure is released, that means delta P will equal to 0, and when the buoyancy is smaller or equal to the gravity, you will create an irreversible situation just like this structure. And for theory part, so for theory assumption, we assume that the air column here is ideal gas, and also the water will be the incompressible fluid, and also we need that the outer water level variation which here, and also the bottom area thickness of the diver here. Because we burn the plastic to make the bottom area of the diver, so we can the thickness will be very small, so we can ignore it in our theory. So this is the force analysis of the diver. So the force working upward will be the buoyancy and also the drag force, and the force working downward will be the gravity of the diver. And for Pascal law, we need to describe the pressure of the air column. So because of the Pascal law, we can know that the pressure of the air column will equal to the pressure in tube. Then we use Boyle's law to describe. So as we know that the pressure multiplied the volume will be constant, we can write the pressure of T equal to the air pressure plus the additional pressure and plus the water pressure. And because of the cross-sectional area of the diver is the same, we can get this equation. So we can get the length of the air column, which here to T will equal to this equation. And because of when we place the diver into the water surface, it will create an initial length of air column, which means the L arrow. So we need to consider it. And when in these situations, the buoyancy will equal to the gravity. So we can write the L arrow equal to these equations, and we will use this in our experiment. So then we need to talk about the balanced height of the diver. So when the balanced situation happens, the buoyancy will smaller or equal to the gravity. So we can describe the buoyancy equal to the law multiplied gravity multiply the volume of the air in the diver. And we can get the balanced height will equal to this complex equations. And then we consider drag force, which will let the diver irreversible height to be more longer. So we get the Reynolds number of the cylinder and get the drag coefficient, and in order to get the drag force. And this is the simulation of the Reynolds number to time in this situation. So in this time range, we can know that our Reynolds number is under 2,100. That means our water is laminar flow, which will no turbulence affect our phenomena. And then we go to simulations. So the reluctant force will equal to the gravity minus drag force and minus the buoyancy. So we can get the simulation of the height of the diver to time and velocity to time and also the acceleration to time like this. Then the most important part in the problem statement is the critical value of depth, so we need to calculate it. So in this situation is when the additional pressure released it, which means delta P equals 0, and the buoyancy will smaller or equal to the gravity, and we can get the critical value of height in this equation by get delta P equal to 0 into the balanced height. Then we use Bernoulli's law to make sure that our theory is correct. So we consider the A point here and the B point here. So because of the, we assume that the outer water level won't change because the variation is very small, and we can get the pressure at the A point will equal to this whole equations. Then we can get the whole flow rate of the diver and also the buoyancy. So we can get a reluctant force which is equal to the gravity minus the buoyancy. And we can get the height to time chart, height of the diver to time chart in this Bernoulli's principle. So we can know that in this two height of theory, the derivation, the result is similar. So we can know that our theory is correct. So for experiment part, equipment, we use plastic tube to let the diver to dig. And we use test tube. We made the test tube in the cylindrical shape to be the diver. And we will more fit our theory. And also use an inflector to add additional pressure, use lead sheet to add the mass of the diver, and use pressure sensor to control the additional pressure. And use support to support it too, and use plastic cap and also a strap cap to prevent from the leak gas. And we also use blow hole of the bowl to add additional pressure to prevent the leak gas happen. And this will be the motion of the diver. So you can see that the inner water level will increase. And then we measure the critical value of depth. So you can see that in our green part, the beginning height will not equal to the final height. That means the diver is in irreversible situations. And for this boundary orange line will be what the critical value of depth we calculate in the theory will equal to these equations. Then the first experiment is about the length of the air column. So we can get the equation of the initial air column, length of the air column, and into the length of the diver. So we just change the length of the diver. It's easier to do our experiment. So this is the experimental result. So you can see that the green circle will be where the diver can be reversible, and the red X will be where the diver is reversible, and the blue line is theory line, which means that the upper the blue line, the diver will reverse. Downward the blue line, the diver will reverse. And also, you can see that when the length of the diver increase, the critical value of that increase. This is because of when the length of the diver increase, the buoyancy increase, and we need more water pressure to put the diver into the irreversible situation. So it will cause the critical value of that increase. And it also fits our theory. And the second experiment is about the outer base area. We burn the plastic to make the outer base area radius, and we control the inner base area. Then this is the experimental result. So you can see that when the outer base area increase, the critical value of that increase. And this is because of when the outer base area increase, the buoyancy will increase, and you will need more water pressure to put the diver into the irreversible situation, and it will cause the critical value of that increase. And this also fits our theory, which the capital A is the outer base area. And the third experiment is about the mass of diver. So we use lead sheet to change the mass of diver in order not to change a lot of the outer base area. And this is the experimental result. So you can see that when the mass increase, the critical value of that decrease. And this is because of when the mass increase, it will need smaller water pressure to put it into the reversible situation. So the critical value of that decrease. So, and this is our equation, which is the mass of diver, and it will have negative correlations to the critical value of depth. So this is the discussion part, which talks about the boundary limits. So we can know that when the gravity is bigger than the buoyancy, the diver will just directly sink to the bottom of the tube. So which means the white flag here. And because of our tube is only 2.3 meters, so we cannot observe the irreversible height, which is higher than 2.3 meters, which that in our experiment we can only see the irreversible situation in this part of area. And for this and this is the length and the mass of diver that we is considered as a parameter in our experiment. Then we need to measure the current possession when the diver is unbalanced. So first we change the time of the additional pressure maintained. So you can see that when the time increase, the current depth increase. It is because of due to our Bernoulli's law theory derivation, we can get that the T will have positive correlation to the buoyancy. And by this two equation, we can get the theory line blue line in our chart. And the second one, description of the current depth will be the additional pressure volume amount. So we change the additional pressure. When the additional pressure increases, the current depth of the diver will increase. And you can see that in our Bernoulli principle theory, delta P will mean the additional pressure, and when this increases, the buoyancy increase. And by this two equation, we can also get the theory line, red line in our chart. So for the conclusion, first, why the diver will be irreversible? This is because of the buoyancy is smaller or equal to the gravity, and we can describe the buoyancy into these equations, and we can now get the balanced height, and we get the additional pressure equal to 0, so we can get the critical volume of depth into this one. And this chart will be the fourth analysis of it. Then this is boundary condition. So as I said, we can only observe the reversible diver in this part, and this part diver will directly stick, and this part is because of our experimental limit, so we cannot observe this. And this is the length of the diver and outer facial as a parameter that we changed. And we can see that the length and the outer facial increase, the critical value of depth increase. It's also all because of when the buoyancy, this to increase will cause the buoyancy increase, and you will need more water pressure to put it into a reversible situation, and which means that the critical value of depth increase, which Maxwell theory. And this last one will be the mass. When the mass decrease, the critical value of depth decrease. And this is also fits our theory, and this is my presentation. Thank you very much.
Thank you. So now the question of the opponent to the reporter, and the reporter answer the question.
Okay, so thanks for the reporter's report. So I have some short questions. So first, you have mentioned your theory has the cross-sectional area. Okay.
Yes. Yes.
So what cross-sectional area do you consider the inner side or the outer side? Because it has a width.
Inner side.
Inner side. Okay. Okay. Next question. So what is the side of your plastic top in your experiment?
What do you mean side?
The cross-sectional area.
Of the plastic tube.
Yeah, you use in the experiment. Yes.
Radius is 2 centimeters.
2 centimeters.
Yes.
So the weight, you change the weight. Okay. So next question. Can you?
Do you mean the test tube or the plastic tube in that? Do you mean the?
We will discuss that.
Oh, okay.
Okay. And next question. Can you turn to page 28? Okay. So can you explain why is the theory line of the length of the diver is bigger, and why is the theory line quite bigger than your experimental data?
You mean that it's just because of the experimental error, and because
so what causes the experimental error? You see?
Maybe because when we change a very little amount of the length of diver, it will change the critical volume of depth very much. So we only do the experiment by every 5 centimeters. So it will cause a little error in this.
So what do you think if the length of the diver bigger, will the error be bigger?
You mean that
The length of the diver become bigger. So will you think the error of the theory line and of the experimental data will become bigger?
No, it doesn't matter in this part.
Okay, that's fine. Okay, so next, can you turn to page 39? Okay, so your red line is your theory line,
Yes, by
And-
these two equations.
and the blue dot is your experimental data.
Yes, yes.
So why is the theory line smaller than experimental data?
It's because of our additional. We use pressure sensor to add
Okay,
additional
so we
pressure.
move to the preparation of the opponent. 3 minutes. Okay, the opponent takes the floor. Takes 4 minutes.
Okay, so I'm the opponent from Chichen High School. So the problem statement told us that the simple Cartesian diver, for example, an inverted test top, is placed in a long vertical top filled with water. So when we increase the pressure in the top, the force the Cartesian diver to sink. When it reaches a certain depth, it never returns to the surface, even if the pressure is changed back to its initial value. What we are going to do is to investigate this phenomenon and how it depends on relevant parameters. So I think the key points of this. So I think the key points of this problem statement is to find the critical pressure that the diver will not go up, and find what parameters cause it won't go up. So this is the report outline. First, they give us the observation video, and which we think is very good because it's very clear, and they give us the clear focus on their problem statement, and they move on to the theory part. The theory part, they consider it as an ideal gas, and for the incompressible flow, and ignore the viscosity, and they calculate for the pressure change, the Pascal series, Boyle's series, and also the Bernoulli's principle, and they apply the theory to the experimental data and give us the clear experimental data comparison. So, and next, so they move on to the setup. The setup is use pump at the top and the supporter, and also the tank, and also the pressure sensor to sense the pressure change of the top. And for the experimental data, it shows us some critical pressure condition and the length of the diver difference and how would it affect the results, and also the outer base area, and also the mass of the diver that will affect the experiment. And so in their conclusion, they give us their experimental data conclude, and also give us a critical condition, means that the buoyancies and gravity go balanced, then the diver will not go up. So their strength is they give us the clear theory explanation and give us the theory line comparison between the theory and the experimental data, which we think is very important for us to understand whether their theory is correct or not. Second, however, it's not clear. So for the cons, they need to show us the set up picture because they only showed out the video. We don't know how they set up, and they have the small error bar between the theory line and their experimental data. So they need to give us the reason and also how they fix their model. And third, they need to more discussion on the experimental data. For this is an example. So next, what Q&A I have asked about is what's the precise properties of the type you use, because they didn't mention in their reports. And next, second, is they measure the cross-sectional area. They say they measure the inner side cross-sectional area. However, their data shows the outer side sectional area. So the third, fourth, the theory line is bigger than experimental data. So we will discuss that later. Okay, so so next we can move on to the discussion point.
Sure. So we have the discussion between the reporter and opponent.
Okay, so thanks for the report again. So first I want to ask about is you consider ideal gas, right? So do you think that but we know that in a real condition this was not the ideal gas. So do you think this will affect your results?
Because of the ideal gas, it won't only affect the volume, it also will affect the temperature. And we have considered it, so we measure the temperature, and we know that the variation is very small. So the relation between the pressures.
So can you show me the line for consider ideal gas and the line for not consider ideal gas?
How do you mean that not consider ideal gas?
It's a theory to apply ideal gas. So you have a theory.
Because, sorry.
Okay.
Because we assume that it's ideal gas, so we didn't get the theory with no ideal gas. We don't know how to
Okay.
derive the theory with no ideal gas.
Yes, but we know that when the diver sinks, the space here will become smaller, right? Meaning will become smaller.
Yes.
And the gas pressure and the gas between this space will become smaller. The gas space. So this means that the most okay.
You mean the pressure here when the so you mean that when the volume becomes smaller, that the pressure becomes smaller?
No. I mean when you land the diver to sink, the space for the gas is smaller, right?
Yes.
So the distance between the gas is smaller, right?
What do you mean?
It's like the muscular.
So you mean this distance?
Yes, it's like when your diver sinks, maybe at first it's here
Yes.
for the water, and when you sink, the space will only be here,
Yes.
and the space become decreased.
Yes.
So means the distance between the muscular will decrease. So this means they have a bigger
So the pressure increase, right?
if pressure increase. So
Due to the molecule.
yeah. So I mean the distance between the musculars will increase. So this means that the ideal gas will not be applicable because ideal gas only apply for no.
Then it's only for theory part.
So,
We use a simple way to describe the theory. And for experiment, of course, the normal situation will not be the ideal gas, but to the theory derivation, we need to do this assumption.
Okay.
That will be easier to derive our
Yes,
theory.
I got the point. So do you see your experimental data? Can you change your experimental data in a theory line?
Page 39.
Okay. Oh yes, 39. So do you think that this small arrow will caused by the ideal gas?
Okay. I can explain this arrow because we use.
No, I just mean that I'm not
No,
this
no,
arrow.
no.
No, this will not be affected by the ideal gas.
For this arrow, not caused by the ideal gas, it's caused by the pressure sensor, because the pressure sensor will have time delay. So you can see that when we get the time delay,
Yes.
this is theory line. So because of time delay, we can move the theory line back to this point, so
Yes.
that it will fit.
Okay.
So the arrow is caused by the time delay of the pressure sensor.
Time delay on pressure sensor.
Yes.
Okay, so I got the point. So can you turn back to the page 28? I think so your red line is your experimental data or can you explain this?
So we do the experiment that we change the water level
Yes.
in every 5 centimeters, and we observe that it will reversible or irreversible.
Yes.
So for the red cross, it will reverse.
Yes.
It will reverse, and for a green part, it will reverse.
Okay, so what do
And
you
the blue
think?
line is the theory.
What do you think for this small error bar caused by?
Okay, because you can see that when we change very small depth of diver, it will
Yes.
cause the critical volume of depth to change. So, and we use a very long tube, and we add the water level. So maybe the small water level difference in here will
Yes.
cause the error.
So you think it's the pressure difference?
No. The outer the water level didn't control that very well.
Oh.
So it will
So
cause
you think it's
another
an
error.
experiment of a
Yes,
small
that's
mistake?
right.
Okay.
Just
So
like run
okay,
around.
so next, I want to ask about is you mentioned your theory. For example, this is the inner side cross sectional area.
I know.
Your model is inner side.
So for capital A is outer side, for small a is the inner side.
So
we both consider it.
You both consider it.
Yes.
Okay, so
And for the experiment of the outer base area, we control the inner base area. So I misunderstand your question in the short question.
Okay.
This is the how the amount.
so the small
of
a is the inner
and we change
inner
it.
side, and the big a is the outer
Ah,
side.
yes.
Okay, so
This chart.
so next, so do you make sure that your temperature control properly in your experiment?
The variation of the temperature is very small.
Yes.
So for the ideal gas, it's important in the pressure and the volume. For the
Yes.
volume.
Okay, so you think the main cause of the different critical pressure is caused by the the space.
Well, what do you mean critical
Uh,
pressure?
do you find the critical pressure? How? So what condition will not go out?
So okay, so because why the diver will be irreversible is when we
The balance between buoyancies and weight.
we let the pressure release, so it doesn't matter that how the critical pressure is.
So okay.
And the important thing is the critical volume of that.
So can you turn to your theory part? The page 1 theory part. Yes. Drag. The drag force.
Drag force.
So can you describe this?
Okay. We use a radial number of cylinder and get the drag coefficient,
Yes.
and which means C here, and we can get the drag force.
How do you measure the viscosity of it?
We just use simulation to run the radial number 2 times, so we can know that the radial number is under 2,100, so it will no turbulence, and we don't need to consider it.
So you don't need to. So you think your
The
theory didn't need to consider drag force.
we talk about it, and the difference caused by the drag force will be small, so we can ignore it.
Okay, so you ignore the drag force.
Yes, we just discuss about this part.
Okay, so can you turn to your Bernoulli's equation?
Yes.
The final page of the series. The final. Oh yeah, that's good. So, next page, or last page. 20. Oh no, 20. Yes. So, okay. So you apply the Bernoulli's equation.
Yes.
So, so why will this equals this? Can you explain this?
This part is for the we assume that this will be the literal plane. So
Yes.
And here won't have the outer level won't change.
Won't change much.
Won't change. So
Yes.
the velocity will equal to 0, h equal to 0. So we can get
Okay.
I got that point can equal to this.
Okay.
Yes.
Okay. And so for opponent's opinion, what do you think the Bernoulli's law will be applied in what condition?
In what condition?
Yes. Is the fluid continuity or the fluid non-continuity?
And the basic assumption that incompressible fluid is for Bernoulli's law.
So you assume the
water
water to
is
be continuous.
Yes.
Oh, okay. Okay. So can you turn to your any page of your experimental data that has the theory line and the experimental data? Any page is any page. Theory line and the next maybe some dots. The page you
You mean the one for the current depth?
Yes, this one.
Yes.
So you have mentioned that maybe here is caused by the mistake, the experimental mistake.
No, I mean the one in this one.
Oh, you mistake is caused by the experimental mistake.
Caused by the
The pressure change, the pressure.
the time lag.
Yeah, the time lag. Okay, so can you turn to page, turn back? Thank you. Okay, so what do you think this point be? Why will it become slow?
Maybe it's the we didn't control time very well, so because of this one. Because for this one is we maintain the pressure in how much time.
Yes.
So the error will be very small compared to this one because we just use we take a video and check the time. So in this point, I can explain that it will be very small
Experimental
error.
mistake or
Yeah.
time lag?
Analysis mistake.
Analysis mistake.
Yes.
So how about the analysis mistake? Can you briefly explain?
We take a video to track the whole process, so we can know the current depth.
Yes.
And also, by the video, we can get the time range. So
Yes.
when we maybe when we check the current depth, use tracker, and you will have some error.
Okay, I
You
got
will
it.
have some error in the analysis.
Okay, so can you let me next because right so your experiment is doing by putting the gas for the constant inside the top. The gas is hot.
Yes. Yes.
So,
Okay, so now the opponents summarize the discussion.
Okay, so in my discussion, first I mainly focus on the ideal gas, whether we need to consider ideal gas, and next we move on to the discussion of their graph, because in their experiment they didn't really much mention why will for example this graph, why will this point become smaller. So in the discussion they mentioned that maybe it's a timeline or the experimental mistakes that cause the graph to be different. So for the conclusion, I think their theory is construct properly and fit their experimental data, because they just have mentioned this point maybe will be a timeline or analyze mistakes. So we have better understanding of whether the experimental data fits the comparison data, and I think both of us did a really good job, and we have better understanding of this topic. Thank you.
Now is the questions of the reviewer, the reporter, and opponent.
I have a question for the reporter. When the diver goes down and has a acceleration, will it cause the pressure to occur at the bottom of the diver?
Will cause what?
The pressure to occur at the bottom of the diver.
We didn't measure the acceleration of the diver because we think that the motion of the diver is not important. The important is the critical value of depth, just like the president said. So when we go down, of course the volume, the pressure here will increase, right?
Do you think the acceleration of the diver is important?
I think it's not important, because what we are focused on is on the bottom of the diver when it moves, when it caused by the pressure change and it moves down to the maybe we can call that the critical point, means it didn't move. So acceleration is not very important.
Okay. And for the reporter, does cohesion and adhesion force of the water in the Cartesian diver affect the experiment? Cohesion and adhesion force.
It won't cause a lot of change in what we are measuring the depth.
Okay, cool.
Because this force is hard to measure, so we just assume this. We cannot measure this force.
The reviewer suggests that next time maybe you should.
Okay, so because we talk about the record, real number, and also ideal good, so our water will have we assume that our water will have the viscosity is very small, will have the variations.
I have a question for both the opponent and the reporter. Why do you think it is isothermal process? Isothermal process. Isothermal.
What do you mean iso?
Like, why do you both assume that the temperature doesn't change?
Okay, so for me, I had also asked the same questions for the reporter, and he answered that the temperature change is actually very small and can be never met. Yes.
So
I have measured temperature. The variation of temperature is very small. The important part is about the pressure in the volume, not the temperature.
okay, and one more.
Yes.
Can you turn to number 28, page 28? And you say that this is caused by
The error of the adding the water level in the big tube.
and another graph, you say that there is
Okay, so now we move to the preparation of the reviewer. 2 minutes. the reviewer takes the floor.
I'm the reviewer of Figure 2 and I'm going to review about the reversible Cartesian diagram. And I'm going to skip the prompt since they both explained it already. Okay, first is the reporter's outline. They explain the Cartesian diagram by using Boyle's law, and they consider it as ideal gas. And they also use Bernoulli's principle and to measure the experiments. And they also consider buoyancy, Pascal's law, and drag force. They use Pascal's law to calculate the pressure, and drag force they consider it to make sure that there's no errors. And in the experiment, they talked about the length of the air column and which is the critical value increase. And they also do in the outer base area, they found out that the critical value increased. And if the mass of the diver changed, the critical value decreased. The first question, the opponent asked that why are the errors caused by? And the opponent asked many diagrams in reporter's presentation, and there are some errors. And the reporters have different reasons. Like the first one is they didn't control the water level very well. And the second is the time lag of pressure sensor. And the third is analysis mistake. And the opponent also asked why did they consider it as ideal gas? And the reporter says that they control temperature, so the deviation is small enough to be similar to ideal gas. And they use the simple part for the theory. The next question, the opponent asked that why won't the temperature change? The reporter said it's small enough so it can be manufactured. And the opponent asked about the drag force. And the reporter said the difference is small, so the drag force is negligible. And the opponent also asked about the Bernoulli's equation, if it is applied in what condition. And the reporter says the fluid is continuous. And now I'm going to talk about the pros and cons of the reporter and the opponent. First, the reporter. They have strong supporting theories that fit the data. And they have good time control in their presentation. And they have diagrams to support most of their arguments, which is very great. And they also consider the drag force. And the cons is that they didn't try to explain the experiment error when they first presented. But in the discussion time, they explained the errors well, and we think that is great. For the opponent, the pros is that they clarify the unclear parts, clarify the diagrams, and clarify the formula, and which is very great. And they do most of this in the 2 minutes, and make us learn about it and clear some explanation. And they also brought out the error in the data. And the cons is that they focus too much on experimental setup and the technical error. And I think they should focus more on the theory or and the reason for the Cartesian diagram. And they should talk more about the physics phenomena. And this is my presentation. Thank you.
Thank you. Now the concluding remark of the reporter.
So why the irreversible diver phenomenon happen is because of the buoyancy smaller or equal to the gravity. And also this critical value of height means the water level. Because the diverting down to the bottom, so we can just get the height is the water level here. And this is the boundary condition of theory in our experiment. So this part is where the diver will directly sink, and this part which we printed after. And also we consider a drag force, and because of the real number of the water is very small, so we assume that the water viscosity is very small, and we can exist in water. So this is where we focus on the discussion very much. And the deviation, the experimental error in the experiment might caused by the duration of the pressure sensor, which is in the current depth chart. Because of time delay, also of the water level. So because in our experiment we can know that the small variation of the outer water level will cause a very big difference in our result. So we have tried it to control the outer water level this water level very well already, but because still will have small variation, it will cause the experimental error in our external charge. Also, the Reynolds number is very small, so the viscosity won't affect the whole thinking. And also, because of the temperature variation is very small that we have measured it, so we will mainly focus on the boil salts in ideal fluid, which means the pressure and the volume relations. When the pressure when the volume decreases, the pressure will increase. And also, we measure the current depth of by a tracker, so you may cause small error. And as I said, the critical volume of depth will equal to, because it's diverging to the bottom, and this part will, water level will be the critical volume of depth. So, in this case, this
you.
will have converted. Thank you.
So now the question of the jury.
I'm wondering the speed you perform the experiment. For example, you gradually increase the pressure. How fast do you increase the pressure? Or if you increase the pressure very, very, very slow, I mean, every situation is a linearly equilibrium condition. And what will happen?
Like on the chart we showed, and we maintain different additional pressure time. So that will correspond to the speed that we press the additional pressure. So we can know that this is for current depth, but in our phenomenon, throughout the experiment that we do, the variation is very slow.
For the component that you mentioned about the temperature effect, do you think it's important in this experiment?
Yes, I think it's important because like I have just asked for a reporter and whether he is considered an ideal gas or not. So he answered he's considered ideal gas. However, in our opponent's view, we think that the gas will be the gas space will be small, meaning the molecules will become smaller, and the force between different molecules will become bigger. And it also means that the ideal gas cannot be properly explain the phenomenon. So when the ideal gas condition is not when it's not ideal gas condition, and the Pascal's law or either the Boyle's law will not go well. Yes, because it considers the temperature is a constant. Yes.
For the reviewer mentioned about the collision force. Do you think it's important in this experiment? What's your opinion?
We think that it can maybe be negligible because it will let some water go into the tube, but it's just like a little water. It can be negligible, but I think the reporter should still consider it like a drag force.
Question from Professor Yomi.
Hi, thank you for the discussion. And I'm interested in the drag force, so I would like to ask all of you what condition or what kind of experiment set up so that we could get the drag force or even for the liquid, the viscosity of the liquid could make a major difference for the irreversible condition. How do you see?
Maybe we can pass soap into the water and can reduce the drag force. I would think we can increase. We can add salt to optimize our experimental center and the water.
Just I mean, at what condition the drag force or the viscosity of the liquid could result a big difference for the irreversible condition? Big difference. If I want to see the result, how did you design your experiment? Or it is impossible that the drag force or the viscosity of the liquids could result in different.
Maybe we can change the material, the fluid, not water, change in other fluid.
Okay, so for my opinion, so I think if because they use water as their liquid, so if we change the liquid, for example, if we change the glue, and the viscosity we know it will become bigger, and this means that the drag force and the viscosity and the Reynolds number. Because Reynolds number have the viscosity term. So if we change the viscosity, not only the drag force will be affected, also the viscosity and also the Reynolds number will be affected.
You know, I'm asking about the experiment setup so that the result could be
Can you rephrase what you just said?
I mean, if I use other liquid so that the viscosity of the liquid is switch and there's the result of the reversible condition could be switch. Is that true? Or is that not true?
I think it's true. Like if you use another liquid, there is the density will change, and the air drag should be and the drag force should be considered.
Thank you.
Okay, so now the grading for the jury. Okay, the score for the reporter, 8, 8, 7, 8, 7, 8. And the score for the opponent, 7, 7, 6, 8, 7, 8. And the score for the reviewer, 6, 6, 5, 7, 6, 5. Okay, so we close the second round and take a 10-minute break.昨天跟今天的记录，问一下气氛。对啊。是啊，你会选别人，对你了解一下气氛。可以帮我问一下，气氛说他们的对答题目这么高？因为我在想说是他的的确很多的中间的规则。我是这个。
Okay, the presentation of the reporter.
Okay, so honorable judges, fellow competitors, good morning. So today I'm a reporter from junior high school. So today I'm going to report problem 5, synchronized candle. So these are outline. First, we will begin with a problem statement, observation video, move on to the theory, the setup, the experimental results, and last, the conclusion. First, it's a problem statement. So the problem is told us that the oscillatory flames can be observed when several candles burn next to each other. Two such oscillators can couple with each other, resulting in in-phase or anti-phase synchronization depending on the distance between the sets of candles. So what we are going to do is explain and investigate the phenomenon. So we will main focus at a different distance and two such oscillators. So this is an observation video. For example, this observation video is an in-phase oscillation, means that both candles oscillate at the same phase. And next is the anti-phase oscillation, means both candles oscillate at a different phase. So let's move on to the theory. So for the theory, we first the mass production and the chemical reaction will be different by different density and a different fluid velocity, and also by different pressure perturbation and also the viscous stress and the background density and the gravity vector will also affect each other. And at the fourth equation, is only for the low match number, which defines as the fluid velocity over the sound velocity. So if we consider it as a low match number, the fourth equation will be good. So the heat release rate per unit value will be affected by the density of fluid and the velocity of the fluid. And next, let's first look what caused the in-phase. So first, the vortex will start to grow on the side of the flame and cause the flame to be deformed. And next, the flame will start to be deformed by the inner shear layer and cause the vortex, and it will start to grow to the flame neck, and the outer toroidal vortex will cause the flame to be pinched off. And when the flame pinches off, there is actually the flame pocket, and this is actually affected by the detached toroidal vortex. And last, it become a new cycle. So this is an anti-phase. So first, it had an initial roll-up, same with the in-phase caused by the vortex growth, and also the flame will start to become a neck because of the toroidal vortex, and inner shear layer will start to grow. And next, the flame deformation and the initial roll-up will have another impact on the other candles. And also, it will form a new flame neck and finally pinch off by the detached toroidal vortex. So what we are going to main focus on is first, the vorticity change of the candles, and second, the toroidal vortex, and third, the shear layer. So first, let's look at the vorticity transfer equation. It's an equation that evolution of the vorticity we define as omega of a particle of a fluid as it moves with its flow. So if it's for incompressible flow, we can assume that the temperature change can be ignored, meaning the fluid density remains constant. And this term d omega over dt means the material derivatives of the motility vector omega, and this mainly means the rate of the change of motility of the moving particle, fluid particle can be described as these two. The first, partial omega over partial t, means the unstable term for the flow, and the derivation and the motion of the fluid particle as it moves from one place to another is actually the convection term. And next, this equation can also equal this equation. So the A term is representing the vorticity change associated with the stretching and tilting effects of flow. And the B term is baroccolinic term, means why the vorticity will generate. And the C term is a gravitational term and is also a main cause why the vorticity will generate. And D term is a diffusion term. So now what you're going to do next is to calculate for total vorticity and shear. So you can see that the definition of the rate of the circulation we define it as the tau can be defined as this. And by applying the Navier-Strauss equation, we can finally gauge how the circulation changes with time by using these parameters. First, the ρ2 is the density of ambient air, ρ1 is the density of the gas at the flame sheet, u is the flow velocity, vorticity, delta velocity, and delta v is the vertical length of the vortex sheet associated with the control mass, means this length, and tau is the circulation of the control mass, and g is the acceleration of gravity, dv is the thickness of the vortex sheet, means this one, and mu is the viscous term. So next, so in my previous presentation, we know that the film will be pinched off by the toroidal vortex. So what we are going to do now is to find the period of flame flickering. We define it as a tau, and your u naught is the initial drain velocity. H of t is the height of the toroidal vorticity that will change with the time, and d is characteristic length. So by defining the circulations in the control mass b, and we can finally find the frequencies, means here, and the Cj is related to the formation of a toroidal vortex. C is related to the detachment of the vortex. And Ri is the Richardson number defined as the buoyancy over inertia. And it will be affected by the ρ2 over ρ1. And if field vectors enter the system through the evaporation of liquid fuel is in our system, and the initial drain velocity could approach to zero compared to the characteristic velocity by gravity, we define as the root of g times d, and the Richardson number will approach infinite. And finally, the flickering of the flame will be proportional to the root of g over d. And now come to the experiment. First, we use self-made box to make a no outside distribution environment, and use phone to take 8.5 times slow motion video and put candles on metal gases to control it properly, also control the distance. And this is our analyzed model. We write a code in OpenCV and Python to measure blue light pixel of each candle. So why do we measure blue light pixel? So first, we know that the flame temperature is approximately 150 Kelvin, so we can more easily observe the flame by analyzing the blue pixel, which is not too bright to see some shocking phenomena, just like the left graph show. In the visible range, the radiation intensity of the blue light is the smallest. So if we measure the blue light, we can find some shocking phenomena, which the red light or the yellow light we cannot find. So this is how we do this. So let's begin with some background definition and observation. So we define the antiphase as when the frame of two red line has the extreme value of this, we define it as an antiphase, and also the in phase. You can see that the in phase we define it as the frame of two lines merely a quarter and have the same extreme value phase. We define it as an in phase, and the dead phase defines as there is no oscillation. And the phase flip bifurcation state defines as there is only one extreme value in the rate range. So that is beginning some background observation. For one candle, the small oscillation will be, and it didn't have a significant oscillation phase. And therefore, so we put three candles together to create a bigger oscillation, and it's actually having four phase as well, meaning it's a more significant oscillation. And this background experimental result of three candles. At least the percent of phenomena appears in within 30 seconds. Okay, so we can see that it's actually very random in every situation. So what we consider is why will it be very random? Because we know that the period of the flame flickering or also the vorticity change is the main cause of the flame become an in phase or empty phase. So we speculate that if 3 candles put beside each other to create bigger flame, both oscillator will already oscillation synchronously because of 2 closed bamboo core. Therefore, the reason why causes both candle to have the oscillation is not only depends on the motility interaction between 2 bigger flames, but also the interaction between 3 closer flames, one that we form a bigger fire. So therefore, we make candles by ourselves by making 3 times thicker wick candle to make flame bigger by ourselves instead of putting 3 candles together. So these are our parameter distance. So this is a table of it. We can see that between 125 centimeter to 2 centimeter, it actually 100% in phase. And this process is by 30 seconds analysis. And for 2.5 centimeter to 3.5 centimeter, it's actually very random, but it didn't have any phase appear. And for 4 centimeters, the empty phase becomes 100%. And for 45 centimeters to 5 centimeters, the 4 phase actually will appear. And the 5.5 centimeters to 9 centimeters, there's only dead phase. So result one conclusion is like this, I just mentioned. So also we find the period of the phenomenon. For example, the in phase, we can see that when the distance increase, the period increase as well, and as well for the empty phase. So why will we become like this? So it's a discussion. According to the formula we induced, we know the flame frequency will be proportional to the low 2 over low 1 minus the roots of low 2 over low 1 minus 1. So for the higher low 2 over low 1 means low 2 the density of ambient air, low 1 means the density of the gas and the flame sheets, the higher frequency oscillation it will be. So it's why the closer the candles, the oscillation will become small, the free period will become smaller. So next, we also do the stimulation part. We use pyrosol. This is a program that can stimulate the heat release rate, density, viscosity, temperature, pressure, and also motility. First, we simulate the density. You can see as the flame starting to grow, the density is starting to grow as well. And what we observe is that between the 2 flames, the density actually didn't change very much. And so for the density of 6 centimeters. However, the density between 2 flame sheets is slightly bigger, a slightly bigger difference than the 3 centimeter simulation. So simulation of density matches our theory. So next, we do a motility simulation. We can see as the vortex, as the flame started to grow, the vortex started to grow as well. And there is the outer toroidal vortex will start to grow up to the top. And for here it has a small toroidal vortex. And so for the 6 centimeter simulations. Okay, so this is a simulation of the motility result. So the outer motility continue to grow bigger, which our theory didn't consider because the main cause of the flame frequency is not caused by the outer motility. So the inner motility will appear, and the oscillation of 3 centimeters is more visible than 6 centimeters, means they're more complicated inner modality. So this is the 3D simulations of the viscosity. We can see that as the air started to grow, the viscosity actually didn't change very much at the bottom of the flame. So here comes the conclusion. First, we successfully stimulate some parameters affect the oscillation through pyrosol. Second, the distance of the appearance of different oscillation modes have been found for candles made by ourselves. Third, the theory is applicable but still need to be quantified in our future research. These are references. Thank you.
So now the question of the opponent to the reporter answer.
So first of all, do you have the experiment data compared to your simulation data?
Oh no, I didn't have it.
Okay, and you said that instead of using 3 candles combining together.
Yeah, we use bigger. We made candle by ourselves.
Yes.
Yes.
Okay, thank you. And in page 11, you said that it's an incompressible flow. Is that correct?
For incompressible flow, we assume that the density didn't change very well. So in our simulation part, we can see that density is actually not changed very good. Okay.
And is your percentage data calculated by the frequency of by the frequency you observe?
You mean the table of the period?
No, the percentage data.
This?
No.
Percentage data. Which page?
When you describe page 27.
27. This?
Yes.
Oh, so this is very random. So we know that the string candles is very random. So we create a candle by ourselves.
You said that the synchronizing motion is random, correct?
No, it's not random. But for this table, it's random. It's because we put 3 candles for a bigger flame. However, when the 3 candles put beside each other, it will already have a oscillation mode, which is not correct for the how the synchronize happen. Because when the synchronize happen, it's actually the vorticity generates in the 2 candles, not the yes.
So, but the problem says that when you put more than 1 candle together, it will become an oscillator. But if
Yes.
you use a bigger candle,
Also,
then
so
that's
we
only 1
define
candle.
okay. So we define the proper state of are 2 oscillatory flames. So we create 2 candles for ourselves. So these 2 oscillatory flames we define.
Okay.
Thank you. So preparation of opponent, 3 minutes. Opponent take the floor.
So, hello, honorable judges, opponents, reporters, and reviewers. I'm the opponent from Legal 2. And today, the topic I'm going to debate today is synchronized candles. So, I'll just skip through the prompt. And this will be an outline of my presentation in the next several minutes. The reporter's summary, the reporter's conclusion, and the threat and weakness. So first, the reporter's summary. They take the vorticity interaction into account, and they estimate the flame induced vortex sheet through the equation, and they measure the blue pixel. They measure the blue pixel to observe more experiment phenomena, and they have simulate the density of the air in their computer simulation, and they also simulate the vorticity of the air, outer air. and the reported confusion. They simulate some parameters like the length, the number of candles, and the size of the candles. And for the trick, I think they have a comprehensive theory, and they change the parameters, and they also use computer to simulate their experiment, and their experiment actually matched their theory. But their weakness are they didn't explain a lot of their equations, and some parts they just skip through it too fast. And there's no comparison between experimental value and theoretical value. And this is my discussion summary. Oh, thank you. I will just skip to the next
So
one.
you go to the discussion.
Yes. So, can you turn to the prompt? Prompt. Yes. Yes. So the prompt says that when several candles burn next to each other, it will combine into an oscillator, and two such oscillators will interact with each other. But when you use a bigger candle, there's only two candles. So each of these oscillators, there's only one candle. But that's not what the prompt says.
Oh, I can explain to you. Why will we use one candle instead? So we know in our previous background experiments, we used 3 candles and put right to each other to create a bigger fire. It's our background experiment. However, when the 3 candles put beside each other, these 3 candles will actually create a vorticity inside 3 candles. This means that the main cause of the synchronization is between this part. But instead, if 3 candles put beside each other, the vorticity is actually affecting this place. So this is actually not the proper statement told us to do. So we use 1 candle to create a bigger fire to find a.
If you use a big candle, that's not an oscillator. It won't oscillate.
No, it will oscillate. It will have an oscillation just as at the table we show. We have shown that when 2 bigger, because we made the candle by ourselves, so we know that the 2 bigger flames put beside each other. The main cause of the synchronization is by the inner vorticity. It's not the vorticity of both flames, because we know that the flame is.
But that's against the prompt. Because the prompt says that this should be an oscillator, and this should also be an oscillator.
No, proper statement only told us that when several candles burn next to each other, so the candles burn next to each other. We define it as this.
No, but I think the problem statement is trying to tell us that this should be an oscillator, because when several candles burn next to each other, it will oscillate, right?
Yes.
So this should be a single oscillator, and this also, but they will interact with each other. And the problem statement is asking you to further investigate this phenomenon.
So I saw your risk is that you think the problem statement told us in this condition and put 2 oscillators together. I'm curious about the opponent's view of why will our experimental data present so random. With the background experiment we do. The background experiment we do this experiment. So we observe. So we observe that the table, the period of how the in phase this one. You mean this one?
Yes.
Oh yes. So we know that the 3 candles put beside each other is actually really random. So we suppose that it's because of the flame. The flame oscillation will have 2 parts. First part, just I have mentioned, is the vorticity of 3 candles put beside each other.
Okay, but the problem statement says that 2 such oscillators, but that's only 1 oscillator.
So I think your definition is not the same as me. So I'm curious about the opponents. How do you think about this? Because we suppose that it's because the 2 close of the candle flame. So how do you suppose? I'm curious about how do you think about this graph? Why will it appear so random?
I think that's the question I'm going to ask you.
Okay.
Why is that?
Okay, so I can explain to you my suppose. So in this, we speculate that if three candles put beside each other, first I have mentioned here we'll have the vortex, and also here, and here is another candle. So it actually has three parts. So we know that the candle put very close to each other is what actually occurs as in-phase synchronization. So means here, the bigger fire here have one frequency, and here have one frequency as well. So we can define one frequency is actually cause the oscillation, so it will become so random. It's with vector.
What about if all the parameters are the same? Do you think the experiment result will be the same?
What's the mix of parameters?
I mean, all the air density, airflow, and every other things are the same.
Oh, I think it didn't matter how the parameters are same, because we can make sure that when candles look
So are
beside
you suggesting that even if all the conditions are the same, it will be another result?
no, it will not be another result.
Then why is it random?
Oh, so
That's not random.
no,
That depends on the initial condition of your experiment.
Okay. So my point is that the three planes put beside each other, even if you control your parameters very well, you can't deny that the three candles will actually have a. Okay.
And can you turn to your computer simulation?
You want the density or
Density.
density? Okay.
So did you measure the air density in your experiment?
Oh, I didn't measure it because for the
So you can compare it.
oh no. Like you can see that the
But that's only simulation.
yeah, it's simulation, but our theory also consider this. The density beside each plane is not,
Does it match the experiment?
but
Your experiment. Did the simulation match your experiment?
we didn't. Oh, so for this program, it's actually it can simulate for our real situation. However, this program has a little bit weakness is that this that this is not the ideal condition. So this is just a simulation. So if we can, because we didn't have any ability to measure the density.
There's actually a way that's called infographic, and you can measure the density of air.
Okay.
So maybe next time you can try it. Okay, it will make your experiment even better. Okay. So, but if you can predict your experiment using the simulation, then why did you do it?
Oh, because like I have mentioned previously, we cannot measure the viscosity or even the flame sheet density in our experiment. So we are trying to do is trying to simulate the condition. So we try our best to simulate the condition and find that the density really didn't change that well in the inner side flame sheet, which is same with our theory. Our theory consider the temperature in the inside flame didn't change. Means the density is remain constant. So imagine our theory.
Thank you.
Okay,
And so what are the different conditions attributed to the in-phase and anti-phase synchronization?
What causes?
Yes.
Okay, so like I have just mentioned in my, just mentioned in my, you mean the theory part?
Yes.
Okay. Okay, so for in-phase synchronization, we know we observe that there's several. First, it was mainly caused by the detached toroidal vortex. Means the vortex that will form a circle, a cycle, and also the vortex will start to grow and cause the flame to be seen, and finally it will be pinched off by the toroidal vortex, and also a detached toroidal vortex, and cause the flame pocket to be formed, and last another cycle begins.
Okay, thank you. So can you explain what caused the death phase in your experiment?
What causes that? Okay, so in our experiment, we find that the 1.5 centimeters to the 2 centimeter distance have their inner phase 100% in phase. So we assume that it's because we know that the motility is actually affected by the heat released by the flame. So we know that when the flame is bigger, the heat release will be bigger as well. So for our candles, our limits are in phase, we assume as 2 centimeters because we know that when the candle is distance is bigger than 2 centimeters, it will actually have the in phase and also the purification state and also the dead phase. However, the antiphase will only appear at 4 centimeters. So we define the 4 centimeters at the distance which antiphase will be increased, and 5.5 centimeters to 9 centimeters, 5% is the dead phase. So this means there aren't any motility just affect the both planes. So they become the dead phase, meaning they didn't have any interaction.
So, why does the candle close to each other? Sometimes become an oscillator, but sometimes not.
You mean this one?
Yeah.
Okay, so for 1.5 centimeter to 2 centimeter is 100 in phase. So we are also curious about why will this become a small random.
Okay, thank you.
Okay.
On page 13, where does the equation come from?
Oh, it's come from you say the volatility change. 13.
13.
14. Oh, it's come from the paper. We are not sure.
Oh, okay.
So we put it in the reference.
Okay. And so, is there a critical frequency for candles to synchronize?
Critical frequencies?
For candles to synchronize?
You mean in phase or anti phase?
Both.
Both? Okay, so we have find a limitation of distance.
Oh, so can you show it to me?
I can do it. This graph, I have mentioned that this is 100% in phase.
Oh, okay.
Yes. So it's a limitation of in phase we define this.
So, did you simulate the airflow between the oscillators?
You mean what kind of airflow? Just airflow?
Yes.
Oh, for airflow. Air value. It's like this. This is actually the airflow. Because in our program, it actually didn't have a vorticity, choose our simulate the vorticity. However, when we observe the flow, how the flow becomes, we find that these three matches are theory assume the vorticity. So because our
So now the opponent summarized the discussion.
So, in a nutshell, I think that the reporter has a different explanation with us about the problem statement, and their simulation can't really represent the experiment data since they can't measure the air density of the air when they do the experiment. But I think they simulate this situation very well. So we can see the theoretical airflow in an ideal condition. So, but I think next time maybe you can try to measure the air density of the above the candles, and maybe next time you can try to add a barrier around the air to see if that will affect your experiment results. And thank you.
Okay, now the question of the reviewer to the reporter and opponent.
So first, I want to ask the reporter, how do you define in-phase synchronization and phase synchronization?
Okay, so so I can quickly draw. So we know that the in-phase really have a period, right? So we define if it's like this, and we define if two flames, this one first wave and this second wave. So we define is the quarter, the red line. So if it had an extreme value of both, this defined as in-phase. So if it has another one value.
I want to ask the next question.
Okay.
If two flames have a negative phase shift, we could still define it as in-phase synchronization.
Okay. This is actually bifurcation state because we define as this place and this is actually out of this place. So when the bifurcation state happens, we define it as only one extreme value of this range.
So when this phenomenon occurs, how do you define this kind of
we assume the bifurcation state is defined as when the in phase, because we observe that the in phase to the anti phase it actually has a period. It is not immediately in phase and change to anti phase. So
there's a process of between. So to the opponent, do you agree with do you agree with that?
I don't agree with it.
You don't agree with it then? And how do you think we should define the in-phase mode and anti-phase mode?
I think there should be a variable number to define whether the two oscillating are in phase or anti-phase.
Okay, thank you. And back to the report.
Yes.
So when the two phases are showing like this in this situation, and you define, as you say, you define this part as in phase, and you define this part as anti-phase. And how do you define? So how do you define the transition between these kind of two phases?
You mean in phase and anti-phase?
Yes.
So we define in phase and anti-phase as bifurcation states.
Oh.
Constant bifurcation. We didn't mention very well in our.
Okay, I got it. And to the opponent, do you agree with that?
I think I agree with it, but I think he should further explain it.
Okay, thank you. And to the reporter, you only mentioned about the thermal convection in your theory. And do you think other kinds of heat transmission, like radiation or the combustion by the flame itself, should also be considered in your theory?
Oh, I think it should be considered because we have mentioned the flame has when the flame becomes bigger, the heat release rate will be bigger. So the main cause of the heat release rate is the heat radiation.
The radiation is going to affect.
Yeah. So heat radiation maybe need to be considered in our theory.
But you didn't consider.
Oh, because compared to the convection, the radiation is small.
Did you do any experiment to ensure that the radiation effect is very small?
Okay, now the preparation of the reviewer. 2 minutes. Now the reviewer takes the floor.
Okay, honorable juries and all the competitors, this is a report from being Selfie, and today I want to review problem statement number 5, synchronized candles. And here's the problem statement. Oscillatory lines can be observed when several candles burn next to each other. Two such oscillators can couple with each other, resulting in in-phase or anti-phase synchronization. Depending on the distance between the sets of candles, explain and investigate this phenomenon. And I think our main focus of this problem will be the main cause for the flames to synchronize, and the boundary of two forms depends on the relevant parameters. And here's the outline for reporter. First of all, the reporter did a very good have a very clear observation video, and have a very clear theory derivation for to show us, and they have simulated phenomena as well. But they are really lack of the other heat forms that they didn't mention in their theory, and they didn't connect their simulation with the actual experimental result as well, and as well as in their experiment, in their theory, they have also mentioned something that that didn't actually compare it to the actual experimental results, and there really lack of parameters. The only parameter that did is the distance between the two sets of candles, and the lack of the experimental data comparing to the simulation results. And here's the outline for the opponent. First of all, they clarify the synchronization of random is not random, and they point out the recorder is lack of some and then they also point out the random motion that the recorder didn't mention. And but the concept of the opponent is that really lack of the discussion of the talking about different parameters, and they're focusing too much on the normal problem statement, but not the experiment itself. And then here's the discussion. First of all, the opponent asks, we shouldn't use a bigger candle because that's not an oscillator. But the reporter said it will change the vorticity, and that's going to affect the result. And the review of the reviewer is if the single candle still oscillates, and then it will fix the problem statement. And then the opponent asks, why is it randomly? And the reporter said there are two frequency influence. And we think they should explain the relations between the distance and how does the percentile of the probability of in-phase and anti-phase occurs, the distribution, the relation between them. And then the opponent also asked did you compare the experimental result and the simulation as well? And the reporter replies no. And we think that they should compare the experimental data and the simulation data in order to find out if the theory actually fits this phenomenon and an experiment. And then here are the pointers of the reporter. First of all, they didn't consider the oxygen concentration change while the flame is burning and flickering. And I think that's also probably going to cause the difference of the result. And they didn't quantify the amplitude of the result and the frequency and the period and also the coupling. And also the coupling strength, they all didn't mention about that part. And other heat transmission like diffusion, conduction, and radiation are all the things that they didn't mention in their theory. And they didn't measure some important factors of the phenomenon, such as temperature or the coupling strengths between the two sets of candles or the brightness. And they defined, but they didn't clarify the definition of true synchronization. And there are really lack of parameters, which like paraffin consumption rate median between the candles can also be talked about. And the vortex, they didn't talk about the horizontal.
Okay, now
as well.
the concluding remarks of the reporter.
Okay, so for concluding remark, first we define in-phase and anti-phase by the first quarter of one period, and we define the transition from the in-phase to the anti-phase as a purification state. And heat radiation, we should need to be considered to our theory. However, we assume that it's too small. And three candles put together to become a bigger flame will affect the result, since the bamboo core put too close to each other, which means there will be an oscillation for the both candles, so it must affect the result. Also, like the opponent's mentioned, we should also measure more density of either the flame or the ambient air. However, we didn't do it in our experiments. We can fix it next time. And next, they both told about we didn't have a comparison between experimental data and the theory data. But I need to say that we have tried to compare between these two data. However, we know that this F is a frequency period. We know that it has very relevant, like the low 2 and low 1, which I mentioned we cannot measure. And also the C is a constant related to the detected flame. So too many constants we cannot measure. So we didn't have a comparison between theory data and experimental data. So for the future work, maybe we can focus on the comparison between theory and the experimental to prove that our theory is applicable and is correct. And so for conclusion for the discussion, I think the opponents gives us clarify some mistake. I didn't say in like presentation. And for reviewers, they really point out the good points we missed, and we need to fix it our theory or also our experimental next time. However, in this experiment, we are trying our best to stimulate the part we assumed in our theory, because in our actual condition, we cannot be measured. They cannot be compared between the theory data. Thank you.
Thank you. And now the questions from the juries. Professor Lee
To the reporter. I have two questions. One question is that in your two-candle experiment, you find that for 4 centimeter, you will always observe the anti-hit phase. Can you explain what does it mean, or what's the what kind of critical length correlated to your 4 centimeter
Theory.
Yeah.
Okay, so first I will describe the in phase first. So I have mentioned that in phase in my theory is because of the same detached vortex and also the toroidal vortex and cause it to pinch off. And so for the antiphase, our theory assumes that when the one flames become bigger by the vortex, the other flames will not be affected by the vortex. So this is why it calls the antiphase. So for our experimental result, we find the 4 centimeters only have the antiphase. However, we cannot make sure that only 4 centimeters have the in phase. Maybe we can try to decrease some centimeters. For example, 3.9 or 3.8, or also increase and find the accurate range. This is what we can do in our future work as well.
The next question is that apparently you have some uncertainty in your experiment because it's especially during the in phase or out of phase distance. What do you think is the main reason for the uncertainty, and do you think is it possible to control?
For example, the in phase to the
you show us that there are many possibilities for different phases.
Okay,
it looks like it's not easy to control, right?
It's not easy to control.
What's the uncertainty coming from?
Okay, we have also investigated this problem as well. So in our discussion, we think that the main cause of the uncertainty, maybe not in phase or either anti-phase, is because when the flame flickering frequency is not the same, and it's actually, for example, for one candle is about 0.5 centimeter will pitch out one time, and for the other will become is 0.4. However, this frequency won't match each other. So finally, when the in phase change to the anti phase, the inner motility change will finally lead to the anti phase of the candles. So the random is because two frequencies cannot match each other very well. It's our assumption.
For the opponent, in the beginning of the discussion, you mentioned you are discussing about the 3 candle or 3 separated candles. Do you think it's important, and what's your reason? Can you explain?
I think it's important because a part of their experiment is actually against the problem statement. So I think they shouldn't use a big candle to represent 3 candles, since one candle cannot operate.
So even one candle, but you have 3 frames, right?
Yes.
Do you think it's still not the same as 3 independent candles?
I think 3 independent candles will cause an oscillation itself, but one candle won't cause an oscillation itself.
For the reviewer, in your question, you are discussing about the definition of in phase or out of phase. Do you think it's critical to this problem, or what's your opinion?
Yes, because only if first we have to define each phases first, and then after that we can know the relation between the relevant parameters and the boundary between different phases.
Question from the jury.
Curious, when you presented the 3 candles, I just want to know, are these 3 candles lined up in the line or like
The position of your 3 candles.
Oh, only a triangle. Because when we put in a straight line, the flame will actually cannot become a bigger flame. It will become like, I can draw for a quick picture. So when the three frame is put like this, and it's actually three frames cannot become the bigger frames. It's also it will become three frames just outside by itself. So we put in a triangle so the bamboo core can put together to each other to create a bigger frame. Yes.
Any other questions? Okay, now thank you. So now the grading from the jury. The score for the reporter 8, 7, 8, 6, 7, 8. And the score for the opponent 7, 6, 4, 6, 6, 7. And the grade for the reviewer 7, 7, 7, 8, 6. Okay. Huh? Oh, okay. So reviewer. So show one more time. Reviewer. 7 reviewer. Okay. The last one. Reviewer. 7, 7, 7, 7, 8, 6. Okay. Any additional comments from the jury to our students? You can speak in Chinese. 有没有各位评审委员有没有什么建议要给三队的同学们？中文没有关系。
是的，给
没有啦，有没有什么 remark？ 我们也是有讲 ，OK。
主要是怕后面会不会再遇到。
好，那就we close this morning competition and thank you very much for everyone's participation and enjoy your lunch break and we will start this afternoon section at 1:30 p.m. Okay, thank you.